This is the first lesson for engineering dynamics, mechanics. So for the next 6 lessons, we will be focusing on the kinematics of a particle, where the word kinematics just refers to motion of the particle. So we're just going to be focusing on the geometrical aspect of the particle's motion. First thing we're going to look at is rectilinear motion with continuous motion. Rectilinear motion is just motion in one direction, so motion along a straight line. In this tutorial, we're going to introduce the concepts of position, displacement, velocity and acceleration. We'll derive the equations for rectilinear motion and we'll complete 4 example problems for you to have a look at. So let's continue on. First we're going to talk about position. So all position is just where the particle is located. You need to know that for rectilinear motion the particle just moves along a single coordinate axis, which in this case I'm calling S, and where it is from the origin is just its position. Okay, so it's the distance from this origin, and the origin, we say that's point 0, and it's the point where these two lines here, they intersect, and the distance from the origin is the position. Now, an important point about position is that it's a vector quantity since there is direction and magnitude. The direction, what I mean by that is that it can either be on the right hand side of this origin, where we say S is positive, or it could be on the other side of it, where S would be negative. That would look like this. So now we're saying S is negative, and the magnitude would just be how far it is from the origin. Let's have a look at displacement now. Displacement is just the change in position. So the change in position is denoted by delta there. That just means change. It's the difference between the final and initial position. If I say the initial position of this particle was S1 over here, and it's moved from this point to that point, that would mean the final position there I'm going to call S2. So if I find the difference between the positions, the difference between S2 and S1, I get delta S. So to find delta S, I'll just do S2 minus S1, and that will give me delta S. So if S2 is greater than S1, that means the displacement will be positive. So we would get a positive value for that. If it was the other way around, so if the particle moved from this point to that point, so now we're saying this is the initial position there, S1, and this is the final position there, S2. Because S1 now is greater than S2, we would actually end up getting negative S. It's important to know from that displacement is a vector quantity since there's direction and magnitude. So the direction would just be either positive or negative, and the magnitude would be how much that change in position is. Let's talk about the difference between displacement and distance. So let's say this particle moved from the origin along this path to where it is now. So the distance it would have covered would have been whatever length it moved along this path, and its displacement would have been its distance straight from the origin to this point here. So if you was to take this path here and stretch it out so that it was straight, you'd see the distance it covered would have been much larger than its displacement. Okay, so that is the difference between displacement and distance. Distance is a positive scalar quantity, so we don't associate a direction with the distance that is travelled. It's the total length of the path the particle has travelled along. So that is the path it's travelled along there, and its displacement would have been just its change in position from the origin to where it is now. Now, if it was to follow this same path on the other side of the axis here, we would still say distance is positive because, like we said, distance is just a scalar quantity, but its displacement would have been negative. Another way we could illustrate this would be to say if the particle started from this point here, okay, so that's our particle, and then it moved along this whole path around here, and then ended up back to where it started from. The distance would be the total length it's covered along this path, but its displacement in this situation would just be 0 because its change in position is 0. Okay, so delta S would be 0, and the distance we're just going to call d. Okay, so the distance is the length of its entire path, and delta S, the displacement, is just its change in position, which in this case is 0. But let's say if we had this situation, so it started from this point and then moved around and ended up, say, at that point there, so we're going to say that's S1 and that's S2. So its distance again would be that length that is travelled around. Okay, so that's the length of the path that is taken, and the displacement, which is the change in its position from S1 to S2, would just be this length from there to there, which I'm going to call delta S. So that is the difference between displacement and distance. Let's have a look at an example to illustrate the difference between displacement and distance. If we have the particle here initially located 10 meters from the origin, and let's say it moved down from that point 3 meters up to where it is now, we want to find what is its displacement. Okay, so we're going to call that initial position it was at, we're going to call that S1, and its final position there is S2. And because it's moved 3 meters from S1 to S2, that would mean at S2 it's 7 meters from the origin. So to find that displacement, we just do S2 minus S1, where S2 would be 7 meters and S1 would be 10 meters. So then we'll just do 7 minus 10 to get minus 3 meters. So the displacement is minus 3 meters. And to find the distance, that's just going to be 3 meters because we know all it's moved is just 3 meters. Now it doesn't matter if it's moved 3 meters to the left or if it's moved 3 meters to the right, we would put down 3 meters for both cases. But for the displacement, if this was S1 instead, okay, if it moved from this point to that point, that will come out as positive 3 meters. Okay, but since it moved from this point to that point, we say it's minus 3. So displacement takes into account what direction the particle's moving in. So let's have a look at another example to illustrate that. So let's say we have the particle starting off at the origin, then it moved 10 meters to the right, and then it moved 3 meters to the left. Okay, so it started off at the origin here, so it went 10 meters and then 3 meters to the left. And we want to know what the displacement is. So we're going to say S1 is its original position there at the origin, and S2 is its new position. So we apply our formula, so delta S equals S2 minus S1, where we know delta S, that's just going to be 7 meters because we know it's moved 10 meters that way, then 3 meters down. That means it's now going to be 7 meters away from its original position, so the displacement would just be 7 meters. So 7 minus 0 would give us 7. But the distance it's travelled, that would be 10 meters to the right, then 3 meters to the left. So the total distance it would have travelled would have been 13 meters. So now we're going to talk about velocity. So velocity is a time rate of change of the particle's position. So velocity is just the rate of change of displacement with time. So let's say now we have this particle moving from S1 to S2. So we can easily get its displacement, which is just the change in those two positions. And if it does that in a certain amount of time, delta t, so if it was here at time 1 and then ended up there at time 2, find the difference in the times, which will give us delta t, and then if we do delta s divided by delta t, that will give us velocity. So velocity is negative or positive depending if the displacement is positive or negative. So if the particle moved from this point to that point to the right, the velocity would come out positive. If it moved the other way, it would come out as negative because the displacement is negative. Time can never be negative. Time is always positive. So it only depends on whether or not displacement is positive or negative. So that would mean velocity is a vector quantity. Okay, so velocity versus speed. So velocity is not the same thing as speed. Speed is a positive scalar quantity, and speed is the rate of change of distance, not displacement. Okay, velocity is the rate of change of displacement. Speed is the rate of change of distance. If the particle started from origin O, ended up at this time here in time delta t, the speed would be greater than the velocity because it had to cover more distance in that same amount of time. If the particle moved the other way, it took the same path on the opposite side of the axis, speed will still come out as positive because speed is a scalar quantity. Let's have a look at a more clearer example. So if I've got a graph here now, on the y-axis I've got position, on the horizontal axis I've got time, and the particle here is located at time 1 and at position 1. And let's say it moves along that arbitrary curve to a new position there. Okay, so it's at time 2 this time, and it's at a new position S2. So we can easily find the displacement, which is just delta S. Difference in position is the displacement, and we can find the difference in time, which is delta t. Find the average velocity, we just do S2 minus S1 divided by T2 minus T1, which will give us delta S by delta t. So if we do the change in displacement divided by the change in time, that will give us an average velocity. And that will be an average velocity moving from this point there, from S1 to S2. If we start to make the difference in time smaller, we start to get closer and closer to its instantaneous velocity at time t1. Okay, so if we keep making that difference smaller and smaller, we eventually end up taking the limit as delta t approaches 0 of delta s by delta t, which will just give us v, which is ds dt. So ds dt is the infinitely small change in displacement by the infinitely small change in time. And that will give us the instantaneous velocity. And we write that as v equals ds dt, which we can also write as s dot, where s dot just means one time derivative. Okay, one derivative in time. So if you see one dot, that means it's been differentiated with respect to time once. So that is the instantaneous velocity. Now we're going to talk about acceleration. So acceleration is the rate of change of velocity with respect to time. Okay, so let's say if the particle is moving from this point to that point, and let's say it's at initial velocity there, v1, and then its speed increased up to v2. And if it does that in a time delta t, that would mean that its velocity has increased, and if we divide the two, we get acceleration. So acceleration is positive or negative depending if velocity is increasing or decreasing. Okay, so if it's positive, that means the velocity is increasing. If it's negative, velocity is decreasing. So let's take that same graph again. Let's say it's at initial velocity v1 at time t1. And let's say at this point there, it's moved to, say, that point. Now it's at a new velocity v2 and it's at a new time t2. So to find the average acceleration, we just do the change in velocity divided by the change in time, delta v is delta t. And if we do the same thing we've done before, we make delta v and delta t start to approach 0. Okay, so we make those differences smaller and smaller. So the more smaller those differences get, the closer we get to the instantaneous acceleration of that particle at time t1. Okay, so if we keep making that smaller, we take the limit as delta t approaches 0 for delta v as delta t, which will give us a, which will give us dv by dt, where these changes are infinitely small. And that would give us the instantaneous acceleration. And we can write that as a equals dv dt, which is equal to d2s by dt squared. So that is the second time derivative of displacement. Or we could write that as v dot, or we could write that as s double dot, where this time we've got two dots there showing two time derivatives. Okay, so now we've talked about position, displacement, velocity, and acceleration. Now we are going to derive the equations for rectilinear motion. So let's continue on. So useful relation we're going to talk about. So first we're going to take the two expressions we had for velocity and acceleration. So we knew velocity is ds dt, and we know a is dv dt. And then what I can do is take this equation ds dt, multiply both sides by delta t to get ds equals v times dt, then divide both sides by v to get dt, rearrange this for dv by multiplying both sides by dt to get that, and then if I substitute dt into there, I get that, and then multiply both sides by v to get this, so we've got v dv equals ads, and that is useful for us for later on. And we could have written this equivalently as s dot times ds dot equals s double dot times ds if we want everything there in terms of s. These are the three equations we're going to use to derive the equations for rectilinear motion with constant acceleration. So the a subscript c there just means constant acceleration. So if we take our first one, dv dt equals a, rearrange that for dv, we get that, and then if we integrate that from v0 to v, and then this side from time 0 to t, we'll end up with this. Okay, so the integral of just dv will just give us v, and the integral for dt will just give us t, where we're holding acceleration there as a constant. And we evaluate these limits, and we'll get this. Okay, so we get v minus v0 equals at. And then I can add v0 onto both sides to get v equals v0 plus at. And that is our first equation there for rectilinear motion with constant acceleration. Okay, so next I can take my other equation, so ds dt equals v, rearrange that for ds, and then because before I found v was v0 plus at, I can substitute v into there to get this. And then I can integrate both sides. Okay, so if I integrate from s0 to s, so the initial displacement to the final displacement, and then integrate this side from 0 to t, I'm just going to get integral of s is just going to give us s, the integral of v0 will just give us v0 times t, and the integral for t will just be t squared over 2. I evaluate these limits and I get this, then add s0 to both sides to get that. So s equals initial position, so s0 plus v0 times t plus at squared over 2. And that's our other equation for rectilinear motion with constant acceleration. Let's take our last one, so v dv equals ads. I just straight away integrate that from v0 to v, and this side from s0 to s. Okay, so I'm just going to get v squared over 2 as my integral there, and just s as my integral for ds. I then evaluate these limits over here to get v squared minus v0 squared over 2 equals a times s minus s0, times both sides by 2, add v0 to both sides, I get v squared equals v0 squared plus 2a s minus s0. And there's my other equation there. So these are the three equations that we found where we're saying movement to the right is positive, and these equations are only useful when acceleration is constant. This equation here, we have velocity as a function of time. For this equation, we've got position as a function of time. And for this equation, we have velocity as a function of displacement. Now these equations, like I said, are only useful when acceleration is constant. So an example of something with constant acceleration is g, okay, so the acceleration of gravity. So we say it's constant when we're making these two assumptions here. So when we're saying the distance from the Earth is small and air resistance is neglected, the downward acceleration is 9.81 meters per second squared on Earth. It varies from planet to planet, but we're just going to focus on Earth. Okay, and that's constant. We say it's constant. Okay, in reality, the acceleration due to gravity actually varies with location and height. But with these two assumptions here we're making, we're just going to say acceleration due to gravity is constant. So now we're going to look at the equations of motion with varying acceleration. Before we were looking at the situation where acceleration was constant. Now we're going to look at acceleration being given as a function of time. So if acceleration is given as a function of time, what we can do is take our initial equation from where it said dv dt equals a, and then we can actually substitute a, which is a function of time, directly into here to get dv dt equals f of t. And then if I multiply both sides by dt, like this, I get dv equals f of t times dt. And then I can just integrate whatever that function is with respect to time, evaluate the proper limits, so v0 to v and from time 0 to t, and I just get this equation there. So after I've evaluated these limits, I get v minus v0, then I just added v0 onto this side. So that's what you do if you get acceleration as a function of time. Let's say we've got ds dt equals v, and then we get ds equals v times dt, and then we integrate ds with respect to s0 to s, and v with respect to time from 0 to t. We get s equals s0 plus the integral of v with respect to time from 0 to t, okay, and then we substitute v into here, we'll get this, okay. So there's two integrals there. So first you integrate this f of t there with respect to time, and then you integrate all of this lot here with respect to time. That is finding velocity when we're given acceleration as a function of time. This is finding displacement when we're given acceleration as a function of time. So in both instances you can see where the function has been put in, and they're both being integrated with respect to time. Okay, so that's what you do if you're given that situation, if you're trying to find velocity and displacement. So what happens if we're given acceleration as a function of velocity? Okay, so now a is f of v, because a now is a function of velocity. So again, we take dv dt equals a, and we substitute f of v directly into there, multiply both sides by dt, and then divide both sides by f of v, okay, because we want to get everything with a v onto one side, because that means we can then integrate or differentiate with respect to dv. But in this case, we want to integrate, so if I integrate, I'll just end up with this. So we get the integral from v0 to v of 1 over f of v equals t. Whatever the function is that we're given, when acceleration is a function of time, we would substitute that directly into there, whatever the function might be, carry out the integration, evaluate the limits, and you'll get time. And what if we want to find displacement? Okay, so we can substitute a directly into there again, and then integrate that with respect to s0 to s, and from v0 to v, and then I'll end up with this. So if I divide both sides by a, because a is f of v, so remember we're trying to get everything with a v onto one side, and I'll make the substitution of f of v into there. Okay, evaluate those limits, and I'll just end up with this. Okay, so if we're trying to find displacement and we're given acceleration as a function of velocity, I'll take this equation, substitute that function directly into there, carry out the integration. Remember there's a v on top, and you can get your displacement. Okay, so acceleration given as a function of displacement. So we've got a equals f of s. We use v dv equals a ds, carry out the integration process from v0 to v and from s0 to s. Substitute a into there to get the integral of f of s, evaluate that integral, so we get a v squared over 2 on this side, then I've multiplied both sides by 2 and then added v0 squared to both sides to get this. So if you want to find velocity where you're given acceleration as a function of displacement or position, you use this equation there, substitute your function into here, carry out the integration process, and then you can find your velocity. So velocity is now given as a function of displacement, which now introduces a new function, v equals g of s. So if you look at this equation here, velocity is a function of displacement, and that introduces a new term, v equals g of s. Okay, so if we do ds dt equals v, and then I replace v with g of s, I then divide both sides by g of s, and then multiplied both sides by dt to get this, so I get 1 over g of s. Carry out the integration from s0 to s, and from 0 to t. Okay, on this side I'll just end up with t, and on this side all I do is just substitute the v equals g of s, so whatever the function is I have for velocity in terms of s, I substitute that into there, and then I can find time. So that function would actually come from here. So if we just square root both sides, okay, I'll get v equals g of s. Okay, so in other words, I'll just square root both sides there, and then substitute v into here, carry out the integration process, and that will give me my time that I'm trying to find. So this is a summary of all the equations that we found. So 1 to 3 equations we use when acceleration is constant. Okay, so these actually have quite limited use, but we will apply them. So make sure you write these down, and you should really know these off by heart for whatever course you're doing. So these are still important, but again they have limited use. And these are all the equations that we found with varying acceleration. So here we have acceleration given to us as a function of time. For this one as well, acceleration as a function of time, acceleration as a function of velocity there and there. For this case, this is when we're given velocity as a function of s. Okay, so remember v equals g of s there. Here we have acceleration given to us as a function of position. Okay, again you should write these down. Okay, so you should be aware of all of these, and we will look into some examples where we will apply these equations. Okay, so now we've looked at the fundamental concepts of position, displacement, velocity and acceleration. We've derived all the equations we need to answer problems in relation to rectilinear motion, and now we are going to complete 4 example problems. So let's have a look at example 1. So a car travels in a straight direction on a road with a speed of 75 meters per second. The driver slams on the brakes and slows down to 15 meters per second in 8 seconds. Calculate the constant deceleration of the car. Okay, so you need to think in this situation, what equation do you need to use? What we know from the question is the initial velocity, so v0, and we know the final velocity there, v, and we know time. So we need to select one of the equations for constant acceleration, which relates all 3 of these. Okay, so if you know what equation to use, I encourage you to pause the video and have a go at this yourself and see what answer you get before resuming. Okay, but I'm going to continue here. Hopefully the equation you selected was this one, so v equals v0 plus ac times t, where the c, subscript c, just means the constant acceleration. Right. So what I'll do from here is just rearrange that for a sub c. Substitute the numbers in, so I know v was 15 meters per second, v0 was 75 meters per second. So we want to pay attention to the units here, so you might notice I haven't actually mentioned any of the units used for position, displacement, velocity and acceleration until now. If you notice, we have meters per second over seconds, so that is the same thing as 1 over s times meters per second. Okay, so we'd end up with meters per second squared. So the units for acceleration is meters per second squared, or meters per second, or you could write this as m times s to the minus 2. If I then put all this into my calculator, I get minus 7.5 meters per second squared. So the constant deceleration of the car is minus 7.5 meters per second squared, where the minus is telling us it's decelerating. That's the important bit. You can actually lose marks if you don't put that minus there. So remember, acceleration is a vector quantity, so it can be either positive or negative. So let's have a look at example 2. A ball is thrown vertically upwards with a speed of 15 meters per second. Determine the time of flight when it returns to its initial position. So it's thrown from the bottom, okay, so from some point, with a speed of 15 meters per second. So that's the speed that it was released with. Okay, and then that's going to go up, and then it's going to decelerate, get to a point, and then fall down again. Again, pause the video, have a go at this. So let's have a look at the answer. So there's our ball there, starting off from the ground. That's then thrown upwards with a velocity of 15 meters per second, and that is our initial velocity, v0. And that's going to go up, and it's going to get to a point where it's going to stop, where the final velocity there is going to be 0 meters per second once it reaches that point where it stops, and then it's about to start falling down. Okay, so while it's moved from this point to that point, while it was being thrown up, it was decelerating the whole time by minus 9.81 meters per second squared. We need to use that equation again. We substitute the numbers in, so v was 0 meters per second, v0 was 15 meters per second, AC was minus 9.81 meters per second squared, and t is what we're trying to find, so we don't know what t is. And then subtract that from both sides, then divide both sides by minus 9.81 meters per second squared. The minuses cancel out, the m's cancel out as well, and the squared there will cancel out as well, just leaving us with seconds. Okay, so we'll be left with 15 seconds over 9.81, which gives us 1.53 seconds. So it takes it 1.53 seconds to go from the bottom here to the top where the velocity is 0. But when it gets to that point, okay, it's going to fall back down. Okay, back down to the ground. Where its final velocity would this time be 15 meters per second, because while it was being thrown up, it was decelerating. But that deceleration has the same magnitude as its acceleration this time. Okay, so it's going to take the same amount of time to get to the bottom, and it will get back to the same velocity it was released with. To find the time of flight, all we'd have to do is just times t by 2, because remember, it takes the same amount of time to reach the top as it does to reach the bottom. So we get 3.06 seconds, and that would be our answer for this question. So let's have a look at example 3. So an object is thrown vertically downwards into a container filled with fluid with an initial velocity of 35 meters per second. Because of the drag resistance of the fluid, the object experiences a deceleration of a equals minus 0.25 v cubed meters per second squared, where v is in meters per second. Determine the projectile's velocity and position 2 seconds after it is thrown. What we need to recognize here is that we're given a as a function of velocity. Our initial velocity is 35 meters per second, and we're trying to find the velocity and position after 2 seconds. So first I'm going to use dv dt equals a, substitute a into there to get this, so dv dt equals minus 0.25 v cubed, and you should recognize this from earlier on. Okay, but this is where we have acceleration as a function of velocity, and then what I'll do now is just evaluate this integral to just get t, and then substitute my function into there, which was minus 0.25 v cubed. I can rewrite this as 1 over minus 0.25 times v to the minus 3. So I've just rewritten the v cubed there as v to the minus 3. What I can then do is just evaluate that integral. So remember, you increase the exponent by 1 and then divide it by the new exponent. So if I increase that by 1, I get minus 2, and then I divide that by minus 2. Okay, so I'm going to get 1 over minus 0.25 times 1 over minus 2 times v to the minus 2. And then I can rewrite the v to the minus 2 as 1 over v squared. And then if I multiply 1 over minus 0.25 by 1 over minus 2, I get 1 over 0.5. And then continuing on. So then what I do now is take out the 1 over 0.5 as a constant. Okay, I can just bring that out of the bracket as a constant. Okay, evaluate the limits. So it goes from v to 35 meters per second, so I get 1 over v squared minus 1 over 35 squared, which gives me t. And not forgetting the constant as well, 1 over 0.5. Okay, so then what I can do now is times both sides by 0.5 and then add 1 over 35 squared. And then I can rewrite this again as v to the minus 2. And then if I raise both sides to the power of minus a half, what I end up with is just v, because minus 2 times minus a half is just going to give me 1. So v to the 1 is just v. And then this side is going to get raised to the power of minus half as well. So whatever I do to one side, I'll do the same to the other side. So that's going to simplify down to this. Continuing on. So now we want to find the velocity when time t equals 2 seconds. So all I do now is just substitute 2 seconds into there, into t. So I get that. I put all this into my calculator. I then get 0.991 meters per second. So that is the velocity of the object after 2 seconds. So by knowing v equals f of t, we can obtain the projectile's position. So we know v here as a function of time. Okay, it's there. So v is a function of time. Okay, so that's v equals f of t. So if we use ds dt equals v, we get ds dt equals this lot here. So I'll just substitute v into there. And then continue on, times both sides by dt. Okay, so if I times both sides by dt, I get this. Continue over here. I then perform the integration. So I integrate ds from s0 to s. I integrate this side from times 0 to t. So for that, I need to use u substitution. So let's continue on. For u substitution, you have to pick something you're going to substitute and call it u. Okay, so in this case, I'm going to call 0.5 times t plus 1 over 35 squared as u. I then take the derivative of that to get 0.5. And then I got du equals 0.5 times dt. So then, just to simplify things down a bit, I'm going to evaluate this integral. Okay, so the integral of ds is just going to be s, and then it's going to be evaluated from s to s0 to get s minus s0 there. So then, what I'm going to do now is actually, because I've got du equals 0.5 times dt, I'm going to do 1 over 0.5 times 0.5 on this side. So I'm going to multiply this whole lot by 1 over 0.5 and then multiply it by 0.5. And the reason I can do that is because 1 over 0.5 times 0.5 will just give me 1. So it doesn't actually change anything. And the reason I want to do that is because I've got a 0.5 there and a dt there. And I can replace this with du. Okay, that's why I want to do that. So let's substitute u and du into there. So I replace 0.5 times dt with du, and then replace 0.5t plus 1 over 35 squared with u. So I'll just substitute those in. Evaluate that integral, so you remember increase the exponent by 1 to get a half, and then divide by a half, which is the same thing as times them by 2. So that's how I get the 2 there. And then what I want to do is substitute u back into there. So remember u was 0.5t plus 1 over 35 squared. So substitute that back in, and that 2 over 0.5 simplifies down to 4. So let's continue on. And then what I want to do is actually evaluate it from time t and 0. Okay, so I just put time t into there, and that becomes 0 there. So that becomes 0, and that's just going to leave me with this. Right? And the reason it simplifies down to 1 over 35 is because this is the same thing as taking the square root. So anything raised to the half is the same thing as taking a square root, and I'll leave this lot how it is. And then substitute s0 into there, which was 0 meters because it started from position 0 meters, and time t equals 2 seconds. Okay, so because we're trying to find this at time t equals 2 seconds. Substitute t with 2 seconds, substitute s0 with 0. It's going to give me this. And then simplify this down. So 0.5 times 2 plus 1 over 35 squared, which is, it just gives me 1, minus 1 over 35 times 4. And that's going to give me s equals 3.884 meters. So that is its position after 2 seconds, which is 3.884 meters. Okay, so let's have a look at example 4. The question reads, the acceleration of a rocket launching vertically is given by a equals 6 plus 0.04 s in meters per second squared, where s is in meters. Determine the time needed for the rocket to reach a height of s equals 1000 meters. Initially v equals 0 and s equals 0 at time t equals 0. So we're given the acceleration as a function of position or displacement. v0 is going to be 0 meters per second. S is going to be 0, so S0 there is going to be 0 at time t equals 0, and these are the initial conditions. So we're trying to find the time taken for the rocket to reach 1000 meters. We need to recognize that acceleration is given as a function of displacement. So I use this equation here, so AdS equals VdV, and then substitute A to there. So I know A was 6 plus 0.04s. Substitute that into there. Evaluate all the limits. Okay, so I'm integrating this. So S0 was 0, okay, because it started off at 0 meters. V0 is 0. And then integrate this to get 6s plus 0.04s squared over 2. That's how we got 0.02 there, because I divided by 2. And this becomes v squared over 2. And then evaluate the limit from s to 0 here, and then from v to 0 there. So this whole term is going to disappear, this whole term is going to disappear, leaving behind this. So times both sides by 2 to get 12s plus 0.044s squared equals v squared. Take the square root of both sides to get v. So I need to relate this equation now to time, okay? And one way I can do that is to use ds dt equals v, and then substitute v into there to get this, and then multiply both sides by dt to get that, divide both sides by this lot to get this, because I want to get everything with an s onto one side so I can integrate, and then rewrite it like this. Okay, that is the same thing as this, but I've just rewritten it as 1 over square root of 12s plus 0.04s squared, and then integrate that from 0 to s and from 0 to t. So for this I'm going to use the table of integrals. Okay, so if you look at the table of integrals on the formula sheet on the website, you'll find this integral here. Okay, so we've got s and s squared, and we've got x and x squared there, and the a in our case is going to be 0 because we don't have just a single constant. So remember, I want to evaluate for this from 0 to s, where I know s was 1000 meters, and I know a is going to be 0. So in this situation here, a is going to be 0, b is going to be 12. Okay, so b matches to 12, and c there matches to 0.04. I then substitute all of these into here, I get this. So all I did was substitute c with 0.04 to get 1 over square root of 0.04, and then I substituted everything else. So I substituted b to get 12s, substituted c to get 0.04s squared, substituted c into there to get 0.04, and then substitute b to get 12 over 2 times square root of 0.04, where c there was 0.04. And remember, s in this equation here, so s matches to x, and s squared matches to x squared. So then from this point here, what I want to do now is evaluate the limits. Okay, so from 1000 meters to 0, and I'll get this. So 1000, I'll plug in 1000 into s there and here to get this lot. And then because that's 0, this term's going to become 0, that term's going to become 0, just leaving behind this one, which is how we just get ln of 12 over 2 times the square root of 0.04. Okay, let's continue on. So I can now simplify this down using my calculator. 12 times 1000 plus 0.04 times 1000 squared. This lot is going to simplify down to 228.351. This is going to simplify down to 200. That's going to simplify down to 30. And this is going to simplify down to 30 as well. And then add all these together to get this. Put that into my calculator, so the natural log of 458.0351 gives me 6.127, and the natural log of 30 is 3.4. Find the difference, multiply it by 5 to get 13.62 seconds. And that is the answer to this question. Okay, so if you found this video helpful and you would like to practice some more questions, then you can click the link in the video description, okay, which will take you to this website here, or you can just copy and paste the link directly into a search engine, like so. And you'll be taken to the home page over here. If you then click on Courses, Engineering Dynamics, and then click on Rectilinear Motion, so this is the lesson we just did in this video. And you've also got the formula sheet here, which summarizes all the equations that we found in this video. Okay, so you've got the formula sheet there, and you've got all the integrals and derivatives at the bottom as well. Okay, so you've got all that information down here. So all the integrals are down here and derivatives, etc. Okay, so if you click on rectilinear motion, you've got the same video here. So this is the video you just watched. Okay, and this PDF here is downloadable. Okay, so this has got the questions, so you can download this PDF from this icon here. And it's got all the questions, so question 1.1, 1.2, 1.3, etc. And it's got the answers at the bottom. The answers are down here. Okay, they're the answers. And this is the course content. So these are individual videos that do the solution to each question on the PDF. Okay, so if you want to practice some more, then you can just download this, or you can just work straight off the website. So if you want to practice, this is the place to do it.